now. Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at Adelaide Uni, and it is summer semester 2022. And this is a revision seminar for Maths 1B. So hello from the past, those watching in the future. I hope it's helpful to you. Okay. So we're going to start by talking about the interval of convergence of a power series. So the first thing to know about this phrase, interval of convergence, is it is a thing that belongs to a power series. So first you have to know what a power series is. So a power series is a series that involves powers of x. It doesn't have to be x, but x is tradition. We okay? Ah. Okay. So first you need a power series. And a power series looks like this. The sum from n equals, it doesn't really matter what's here, up to infinity of something times x to the power of n. And there can be anything in this spot. And it is usually a formula involving n. And so most people would call it an, or bn, or cn. It doesn't really matter. It is a formula involving n. And most power series start at 0, but they're allowed to start at 1 or 2 or 500. It doesn't matter. So that's a power series. And the series is referring to the fact that it's an infinite sum. And the power is referring to the fact that it's made of powers of x's, each term. So this is short for this. You know, a0 x to the power of 0 plus a1 x to the power of 1 plus a2 x to the power of 2 plus and so on forever. So this is a short version of this. Trying to get the focus right. That's the best I can get. Okay. So that's what a power series is. And it can be, this an can be anything. It can be a list of numbers. It can be, it's usually a formula involving n. It can just not be there at all because it's just all the number 1. So power series. So, you know, for example, you could have that's a perfectly good power series. And that would be short for this. So when n is 0, I get 0 x to the 0. And when n is 1, I get 1 squared over 1 factorial plus 3, which is 4 x to the 1. Then I get 2 squared, which is 4 over 2 factorial, which is 4 over 5 x squared, and so on. So for each n, that's when n equals 0, that's when n equals 1, that's when n equals 2. And for each n, you can create a term in the series. So this is a term. Okay. That's power series. So that's great. Lovely. So what this means is for every, so that's that. And because it's got an x in it, it means it's basically a function. You can take a value of x and you can put it in this spot, and what it will produce is a series. So each n produces a different term of the series, But if you change the value of x, you'll get a whole different series for each value of x. And so there'll be sometimes, I'm just going to make a simpler one. It doesn't actually just have to have an x to the power of n, it just has to be able to be written that way. So we can say that when x is 0, for example, we get the sum from n equals 0 to infinity of 2 times 0, which is 0 to the power of n. And that's a perfectly good series. And it is 0 plus, actually technically 1. So it's 0 to the power of 0 plus 0 to the power of 1 plus 0 to the power of 2 plus and so on forever, which is 0 to the power of 0 is 1 when you're doing Taylor series. In other situations, it's undefined, but when you're doing Taylor series, 0 to the power of 0 is 1, just so you know. And when x is equal to 1, I get this. 2 times 1 to the power of n, which is 2 to the 0 plus 2 to the 1 plus 2 squared plus, which is 1 plus 2 plus 4 plus forever. And this isn't a number. If I keep adding on bigger and bigger and bigger numbers, I'll just keep getting as a total bigger and bigger and bigger answers. And so this is not a number. If you want, you could call it infinity. And if I tried x equals a half, I'd get n equals 0 to infinity 2 times a half to the power of n, which is n equals 0 to infinity 1 to the power of n, and 1 to the power of n is just 1. And so I get 1 plus 1 plus 1 plus forever, which is also not a number, because it's infinitely many ones added together, that's just infinity. And you could try all different numbers for x, and you'll get all these different answers. Sometimes there'll be an actual number as the answer, and sometimes there isn't an answer because it isn't actually a number at all. And so this idea of something not actually being a number is the formal version of this. This is what I'm calling it. You know, I say, this is what David says, not a number, but the formal terminology for that is does not converge. Or if you like, diverge. They mean the same thing. Diverge in English means move apart, which is strange for this. But what it's moving apart from is any finite number. So, yeah. So different x's will produce different, so this one does converge. Different x's will produce different series, and those series will either converge and be a number, and you may or may not know what that number is, or they won't converge and they won't be a number. And so in a sense, it's like a function, but instead of producing the answers numbers, sometimes it produces nothing. But it doesn't produce nothing, it still produces this set of symbols. So the long version of this is that we have an x and we put it into the power series. So a specific value of x. We put it into the power series, and the series that you produce will either converge or not. So there's two results that could happen. And if it converges, then after it converges, then you could find out what number is it. We're really interested in power series because they tend to come up when we do Taylor series of functions that we like. So that's that. I'm going to stop. How are people feeling? All good. All right. So just so I've got this absolutely clear, for this function, this example here, when x is 0, the answer is, sorry, here we go. It's going to be converge, not converge. So here when x is 0, the answer is converge. And here when x is 1, the answer is not converge. And here when x is a half, the answer is not converge. So somewhere between 0 and a half, putting in an x will switch over between things converging and things not converging. And I also know that when I go down here to minus a half, it does converge there. So what's actually going to happen is that you could try something in all these different values of x, and some of them will converge and some of them won't. Now, this is a picture not of what the answer is, but just about whether the answer is converge or whether the thing you can say is converge or not converge. And so what will happen is that there'll be all these x's that will produce the result not converge, and there'll be all these x's that produce the result converge, and there'll be all these x's that produce the result not converge. And we would like to know what is this? This interval that goes from minus a half to half, I know that because I set it up that way. How do we figure out which x's make it converge and which x's make it not converge? And the theory of power series tells us that this collection of ones that make it converge is always an interval. It's not like there's just random ones in the middle of nowhere that make it converge. All the ones that make it converge will all be together in an interval, which could be either narrow or very wide. It could be just the middle and there's only one number that makes it converge, or it could be everything entirely, but most of the time there's an interval. How do we feel about that? This thing is called the interval of convergence. That is not how you spell convergence. For this power series. Right. So the theorem goes, this is, I don't know what it's called. I don't even know if it's in your notes. The theorem says that if you have a power series, a n x to the n equals 0 to infinity, it doesn't have to be 0. The set of values of x where the series converges is an interval. Even better, actually, let's just adjust that a bit. If your power series looks like this, where it's x minus c to the power of n, the set of values of x where that series converges is an interval with center, whatever that number c is. That's the theorem. I don't know if it's in the notes, but it is definitely the truth. So for this one, the center is 0, because that makes the thing inside this power of n a 0. And the radius is the distance from the center to the edge. So this radius is a half, because the distance from the center to the edge of the interval is 1/2. So that's just from terminology. That's the theorem. The terminology, the distance from center of the interval of convergence to the edge is the radius of convergence. It's called a radius because it's the distance from the center to the edge. That's what it is for a circle. I mean, I guess you could say that the whole width of this would be the diameter of convergence if you wanted. It's not like a thing. We don't have that terminology, but that's what it would be called. And it's even more radiusy when you're using complex numbers because complex numbers are on a plane and you actually make a circle. So if you're using complex numbers, then you get a circle of convergence, which is really cool and terrifying as well in other ways. So if you ever study complex analysis 3, then you'll learn all about that. Yeah, that's a third-year course. And it's the only bit of it I remember. So, okay. So that's what it is. And what that means is that we can actually know quite a few things about a series just knowing that the interval of convergence is an interval. And just know that that interval can be infinitely big. It can be the whole of R, which is also an interval. It's from minus infinity to plus infinity. Okay, so for example, this is one of my favorite things. Suppose n equals 0 to infinity a n x minus 4 to the n converges when x is equal to 2 and does not converge when x is equal to 7. I'm just not telling you what the AN is. I'm just telling you one place it converges and one place it doesn't converge. So this isn't, I mean, it might, I could make up an exam question that went with this, but I'm just thinking about it. So here we are, here's x equals 4, that's the center. And I know it converges down here when x is 2. Converge, not converge. It definitely converges when x is 4 because that's the center. Because when x is 4, it's just a whole lot of zeros. And when x is 7, which is here, it does not converge. So since it's an interval, it definitely converges everywhere in between here and here. And since the center of the interval is 4, it definitely converges all the way up to here. But that's all we know so far. We definitely know it diverges here at 7. So it's possible that the interval of convergence could go all the way up to and not include 7, but we don't know. And it's possible the interval of convergence could go all the way down to 1, but it definitely couldn't go past 1 because it diverges here. So if it diverges at a particular spot, it has to diverge for everything after that. And if it diverges 3 away, it's going to have to diverge for everything after here. But we don't actually know. It might converge exactly at 1 because it's only before and after. We don't know what happens at a particular spot. So my interval of convergence is any interval that's sort of between 1 and 7 and centered on 4. Any of those could be the interval of convergence. And that's a lot of information for just 2 numbers. I think it's cool. So if I ever wrote exams for this course, which I will never do because I'm not one of the lecturers for this course, I would give this and then say, does it converge when x is equal to 3? And the answer is yes. Because it's an interval and it converges for 4 and 2, it has to converge for everything in between. Does it converge for x equals 5? Yes. Because it converges for everything here, it has to converge for everything on the other side too. So that's just silly, but I like it. It's one of those. It just reminds me of Sudoku or Wordle or something, one of those things where you've got a few clues and you can figure out the rest. So physics people love that sort of thing. You know, in physics where they go, oh, it's like, this is the initial velocity and this is the final velocity and this is the acceleration. How long did it take? Or this is the initial, this is the final, and this is the time. What was the acceleration? You know, so they love that sort of thing. So yeah, I think it's a standard thing. Yes? We just don't know. It might converge there, it might not, but we don't have enough information. Yeah. So if someone asked me what's the interval of convergence, I would say the interval of convergence could be any interval within from 1 to 7 centered on 4. So it could be this, it could be this, it could be this, it could be, yeah. Oh no, it's centered on 4. That's at least 2 wide, right? Because it has to be. At least radius 2. So there's not that many options for what it could be. Because it could be 1.5. We don't know where it switches over from one to the other. So this is pretty abstract, this one, but I like it. So here's a question. How do you figure out the interval of convergence if you actually know what AN is? And what we have is we have to use the tools that we know about how to tell whether a series converges, but be able to do them when we don't know what X is. So the tools we have for dealing with series, you know, how to tell if a series converges. You know, step 0 is it's just one that you happen to recognize. So for example, you might recognize, you know, the sum of 1 on n, which is harmonic and doesn't converge. And that's just enough. You say, oh, that's a harmonic series, doesn't converge. You might recognize, you know, 1 over n to the p, which is a p series, and it converges when p is greater than 1. Or you might recognize one of the classic Taylor series and go, oh, you know, x to the n over n factorial. And you'll go, it's the Taylor series for e to the x, and that always converges no matter what x is. Sweet. These are not that helpful for power series. This one doesn't have any x's in it at all. This one's got x's, but it's, you know, a specific one. And so unless that's the exact one you see, it's not going to help. Okay. So the next one is that you can tell when it definitely doesn't converge. So if you've got a series that just has AN, and that might include an X inside it, but it's just like that, then that converges, well, if the limit of AN isn't 0, so AN does not approach 0 as n goes to infinity, then it does not converge. All right, so that's how I knew this one, for example, doesn't converge because the individual terms, each of them gets bigger and bigger. It doesn't go to 0 as n goes to infinity, so it doesn't converge. This does not tell you when things do converge, it only tells you when they don't. So if AN does go to 0, it might converge or it might not. Sorry. But if it doesn't, it definitely does not converge. And then the second thing is specifically for alternating series. If you've got -1 to the n times something, if you can rewrite it in that format. So first you need the terms to go to 0 as n goes to infinity. And you also need sum n bn is more than bn minus plus 1, and that's more than bn plus 2 forever. It's decreasing. Each term is bigger than the one before it, then it converges. And this is called the alternating series test. Only works if there's a -1 to the n in there. There could be -1 to the n plus 1. Doesn't really matter what this is here as long as it covers every number one at a time. If you have -1 to the 2n, that'd just be 1, because -1 -1 to 2n doesn't work because that's the same as -1 squared to the n, which is 1 to the n, which is just 1. So it's important that the thing here is just n or n plus 1 or n plus 2 or n minus 1 or something like that. Something that, if you put in the different values of n, produces numbers one at a time. Stop there. How do people feel about these tests for convergence so far? What about in the Zoom? If you're feeling okay, you can mute this, click the thumbs up sign. Don't forget, this is your seminar. You can interrupt me if something turns up that you want to talk about, okay? Sure. Just let me, before I go too much further, I should definitely try and make sure my pages are in some sort of rational order. All right. It's going to take me a while to think of it. So. Sure, probably made it hard for myself, but here I am. So if I was going to see if this one converges or not, the first thing I would check is to see if the individual terms go to 0, even before I thought about it being an alternating series. I mean, I can see it is an alternating series because it's -1 to the n. But that rule number 1 that I said, which I believe in the notes is called the necessary condition for convergence. Elsewhere in the world and in textbooks, they often call it the divergence test because it can only conclude whether something diverges. And it's not one of the ones I recognize. So yeah, I'm just going to have to leave it. First, I have to see if the terms are going to 0. And so I'm going to need to do the limit as n goes to infinity of n over 2n squared plus 1. I can see that they're both polynomials and the numerator has a smaller power of n than the denominator. And so it should go to 0 because the denominator is bigger. But to be absolutely certain, normally what you do is you divide both the top and the bottom of this fraction by the biggest power of n that is there. And so this would be, that's an n squared. So I'll divide the top by n squared and the bottom by n squared to get this. And the reason you do that is the only limit as n goes to infinity that you actually know the answer to is 1 over n. And the limit as n goes to infinity of 1 over n is 0. And the limit of n goes to infinity of 1 over n squared, well, n squared also goes to infinity, so that's also 0. And this is 0. 0 divided by 2 is still 0. And so yes, that's good. That's the first half of the alternating series test. Well, technically it has 3 parts. First, it has to be an alternating series. And then this has to be true. And then also we need each term to be smaller than the one before it, which is harder. You just have to stare at it, I guess. The denominators are increasing. And so I would say that they do decrease eventually, but you could also graph it. Well, that's the first thing, it is an alternating series. Because of the -1 to the power of n. That's important. Good move to write that on the page. Thank you. So then the last thing is to convince ourselves that this is decreasing as n increases. That's what we need to show. Yeah. Let me think about that. Guess I could differentiate it with respect to n, and then if the derivative was negative, that would make it decreasing. That's one way. Seems like overkill, but you never know. I guess the other way would be possibly if the top was constant and the denominator was getting bigger and bigger, then it would definitely be decreasing. Let me do that. So n over 2n squared plus 1 is 1 over 2n plus 1 over n. I've divided the top and bottom by n this time instead of n squared. And that denominator is getting bigger and bigger as n gets bigger. Because it's approximately the same size as 2n. And the 1 on n is getting less and less. And so that's making less of a difference. Okay, so 2n plus 1 over n increases as n goes to infinity. So therefore 1 over 2n plus 1 over n decreases. And so since the terms decrease and the limit is 0 and it's an alternating series, therefore this converges. A point I want to make very carefully here is that the thing that converges that we're talking about is not this, it's this. This is the running total of this. So if I think about when n is 1, what the answer is, and what it is when n is 2, and add those two answers together, and when n is 3, we add on the next answer, and when n is 4, we add on the next answer. Those totals, that running total, that converges. That's what we mean when we say that the series converges. If it was just this, then we would know that sequence converges because it has a limit. But when there's a series, the thing we're talking about converging is the running total. Running total will get closer and closer to a specific number. I don't know what that number is, but it does exist. How do we feel? This bit for me is always the hardest bit. This bit here, where I show that this is definitely decreasing. And in almost all examples, you'll see people doing it. They just wave their hands and go, oh, it's decreasing. But derivative's not the worst plan either. I could have done or d on dn of n 2n squared plus 1 is, damn, it's quotient rule, isn't it? Okay, so we differentiate the bottom, no, keep the bottom, don't we? 2n squared plus 1 times the derivative of the top minus keep the top and differentiate the bottom, be 4n divided by the bottom squared. Okay, and then the top is 2n squared plus 1 minus 4n squared, so we get minus 2n squared plus 1, which is negative if n is big enough. Therefore decreasing. That'll do. Yay. Wow. Yeah, so this is the hardest part, convincing someone that it's decreasing as n gets bigger. Because the problem with the alternating series test is if it keeps on, it might decrease sometimes and then go up a bit and then go up a bit. If it keeps on going up a bit, then you can't be sure it converges. So All right. And then, so this one still doesn't really help very much. I mean, it helps a bit, right? Because if we had an x, because we're thinking about a power series and subbing an x in, if that x was negative, then it would produce an alternating series because it had a -1 inside the x. Like it'd be a minus x to the n, minus number to the n would be a -1 to the n times number to the n. And so that'd be great. But I'd still have to be sure that the rest of it is decreasing even when there's an x in it that I don't know. Oh, crap. So hard. But there is one general series convergence test that does help, and it's the ratio test. And the ratio test says that if you have a series like that, and if you do this thing, you get each term and you divide it by the one before it. So an is a term and an plus 1 is the term after it. So this is a later term divided by an earlier term. So if you have a later term divided by the term one earlier, and you do the absolute value of that, and you do the limit of that as n goes to infinity, that calculation, if this calculation comes out to be less than 1, then the series converges. If this calculation comes out to be greater than 1, then the series diverges. And if this calculation comes out to be equal to 1, then nobody knows. So I call it the test failing, but like the test failing doesn't mean it diverges. It means the test fails to produce an answer at all. Yep. If the test fails, you have to use a different test. In general, if the test fails, it almost always means that this one doesn't work, that the terms don't go to 0. So, or not. No. If the test fails, it's usually one of these actually, or something close. So the problem is if the test fails, you haven't been taught all. There's like 15 different series convergence tests, and you've only got 4. And the 0th one isn't really a test. It's like, I happen to recognize this series. So you've only been taught 3 series convergence tests in Maths 1B, and there's a lot more of them, and you would have to use those instead. And so they won't give you those in this course, ones that can't be dealt with the ones that you've got. Yeah. So there you go. I'll give an example. So this ratio test is really useful because I can do this calculation with an unknown x. The other ones I can't do that calculation if I don't know what x is, but this one I can do. And so what I can do is I can say, well, whichever x's make this answer less than 1, they're the x's that definitely make it converge. And whichever x's make this answer greater than 1, they're the x's that definitely make it diverge. And if there's any x's that make it equal to 1, I'm going to have to make a separate decision for those. That's the theory that we're going to be working on here. Right. I just want to show you a quick example of the ratio test failing, of not producing an answer. This. The sum from when n is equal to 1 to infinity of the fraction n squared plus n divided by n to the 4 plus 5. I know that this series does in fact converge because I know some things. But the only tools you have in Maths 1B will not allow you to make this decision. So this series the reason I know it's converging is approximately n squared on n to the 4, which is 1 on n squared, which is this one. And so that's why I know it converges. And there's a formal thing like that called the comparison test, but it's not technically in Maths 1B. But just so you know, if it is a polynomial, a rational function like this, and the bottom polynomial has a properly at a power that is at more than one more than the top power, at least one, it could be 1.5, it doesn't matter, then it will converge, the series. Okay, so if I do the ratio test on this, so I know that AN is going to be this. So if I do AN plus 1 divided by AN, all right, so this is AN here, and AN plus 1 is n plus 1 in those positions. So what I've done is I've taken this fraction and every place there is an n, I've replaced it with n plus 1. It's really easy if you're not paying attention to not replace this n with an n plus 1. It's really common for people to forget to replace the one that's all by itself. Just keep an eye out for it. It's a common mistake. And then I have to divide these and I'll get some wicked formula involving n. And then I have to do the limit of that as n goes to infinity. So when you divide fractions, one way of dealing with that is to turn the bottom fraction upside down and multiply instead. And I'm going to do something that's really important and is a very useful trick when you're doing the ratio test is this. Move the fractions around a bit so that the things that are most similar are on top of each other. This is all multiplication and division. I can divide by this n squared plus n either late in the piece or early in the piece because everything's multiplication and division. So I'm allowed to switch these and it will be the same answer. And the reason I've done that is because this is that this n squared plus n and this n plus 1 squared plus n plus 1 are the most similar to each other. They're the same function, but with one's got an n and the other one's got an n plus 1. And same over here. So if I do a limit, if I can do the limits of these two bits separately, if that's possible, then you can do that. So like if it's possible to do this limit and if it's possible to do this limit, then it's okay to do them separately. Okay, cool. Watch closely. Ready? Look at this. If n is like a million, then 1,000,001 squared is not that different from 1,000,000. These two things are going to be almost the same if n is very large. And these two things are going to be almost the same if n is very large. The limit of this bit is going to be 1, and the limit of this bit is also going to be 1. The formal version of that is to divide the top and bottom by the biggest power of n that you see. If I did expand this out, I would divide by n squared. There would be an n squared in it. So if I divide this top of this and bottom of this by n squared, I will get, so n plus 1 squared divided by n squared, because they're both squared, I can divide by n on the inside. And this one, I'll divide the top and bottom by n to the power of 4. So this will be 1 plus 5 over n to the 4. And this one will be, well, it's an n to the power of 4, and I divide by n to the power of 4. But because they're both power of 4, I can bring that, I can factorize that into the division. And so I'll have a 1 plus 1 on n here. And now if I do the limit of that, as n goes to infinity, I'll get 1 plus 0 squared plus 0 plus 0 over 1 plus 0 times 1 plus 0 over 1 plus 0 to the 4 plus 0, which is 1 divided by 1 times 1 divided by 1, which is 1. The ratio test tells me nothing. I do not know if that converges or not. Sorry, guys. The reason I made this illustration is that if you have a rational function here with a polynomial on the top and a polynomial on the bottom, this will always happen. So if you've got polynomial divided by polynomial in n, it makes not the slightest difference what those polynomials are. If you do the ratio test, you'll always get the answer 1. Because exactly of this thing happening, you'll be able to line up the ones that have an n plus 1 and an n, and you'll be able to do that, divide by the highest power in both parts, and it will always produce the same result. So that's the only rule I have for don't try the ratio test, is that if you see polynomial divided by polynomial, don't try the ratio test, because you're guaranteed to get exactly 1. I hope that's a useful thing to know. But I am also hoping that seeing some of these moves that I made were useful. What I would like is for someone to ask a question if it's in their head, or think, if someone watching this had a question, what would it be? Have you got one? You might not have a question, but I'm wondering if you could imagine a question that someone might have. That's okay. It's a useful thing to do for yourself, but it's also a useful thing to do for the benefit of those who are not brave enough to ask the question they really have. If you can think of one that someone might ask, you can ask it. Okay. Right. So I haven't actually got to the interval of convergence yet, but I just thought it was important. So I hope it was okay to talk about this. It's too late now, I guess. So the ratio test is going to be able to tell us which x's definitely make it converge and which x's definitely make it diverge, except a couple where it's going to come out to be exactly 1. And we're not going to be able to use the ratio test. I'm going to have to use one of those other things. Find the interval of convergence for here we go. Let's just make it really fun. This is technically a power series. It can be rearranged to have that 2 outside here. So I know where the center of this is, which is the one that makes every term 0. So if x was a half, that would make every term equal to 0. And so that's the center. Just for future reference, I can do that. Not that it's important, but that is important, but that's where the center is. Okay. So I'm going to find the interval of convergence for this, which means I need to find which x's make it converge. And technically, which x's make it not converge. And so the ratio test is one of the easiest ways to do that, because it's the only one of those tests I can use with an unknown x. And so I'm going to do the ratio test. Okay. So I'm going to call this thing an, all of it, including the x's. I'm going to call all of that an. I know that when I defined a power series, I said it was an times x to the power of n. You can call them whatever you want. And so today I'm calling an the entire thing, including the x's. If I'm in a really careful state of mind when I'm teaching this, I usually call the coefficient bn so that I don't get confused, but anyway. So here I am. And so that means that when I do the ratio test, I'm going to need to know an plus 1 divided by an. Out of space there. Like that. So now I'm going to do the same trick I did last time I did the ratio test. I'm going to turn them upside down, but I'm going to try and put things together. I don't usually succeed at doing this in one step, so I'm not going to. So I've got and this is technically on the top of that fraction because that's what it's multiplied. When you multiply fraction times number, the number ends up on the top. So that's going to be down here. So it's totally okay to skip this step. But if you find that you make mistakes when you do that, then it's also okay not to skip that step. And so I can rearrange this now. I've got an n plus 1 factorial divided by an n factorial. I've got an n squared plus 3 divided by an n plus 1 squared plus 3. And I've got a 2x minus 1 to the power of n plus 1 divided by 2x minus 1 to the power of n. I'm going to explicitly put that in just so that it's clearer what's happening. So if you want to skip straight here, I can see that things that were on the top of the fraction are on the top still. And things that were on the bottom of the top are on the bottom. Things that are on the top of the bottom are on the bottom. Things that are on the bottom of the bottom are on the top. That might be completely meaningless to you, but sometimes it helps people to have a mantra like that. Yeah, I almost always get it wrong, so I just write the fractions out. And I've carefully moved them so that the similar things are next to each other. So, one step at a time. I'm going to start at the end here. Yes? Oh, thank you, 2x. Excellent. So 2x minus 1 to the power of n plus 1, 2x minus 1 to the power of n. Anything to the power of n plus 1 divided by the same thing to the power of n is that thing to the power of 1 because you subtract the exponents. So this bit is going to be 2x minus 1 because we subtracted these exponents here. In the same way that 2 cubed divided by 2 squared is just 2. This one, we know what's going to happen to that when we do this limit. That's going to become 1 eventually. But I might as well do it now. Divide the top and bottom by n squared. That's what you normally do for a fraction like that. And this one, well, n factorial is what you get when you multiply 1 times 2 times 3 times all the way up to n. And n plus 1 factorial is what you get when you multiply 1 times 2 times 3 times n plus 1. And so this includes everything that does as factors. And so this is n plus 1. So just a useful rule to know that n plus 1 factorial divided by n factorial is, in order to make n plus 1 factorial, first you have to multiply everything from 1 up to n, and then you also have to times by n plus 1. So n plus 1 factorial is the same as this. And so then they cancel and you get n plus 1. That's what was going on in my head. And I should not have done this because the radius of convergence of this one is 0. Okay. This is bad. I'm so sorry. The limit as n goes to infinity of the absolute value of an plus 1 over an is the limit as n goes to infinity of the absolute value of n plus 1 . Oh, crap. Can I just not write that working? It just is annoying me. I shouldn't have done this. I know I need to do it eventually. Damn it. It's all right. Just going to do it. Committed to it now. So when I do the absolute value of this thing just here, the absolute value of n plus 1 is still n plus 1 because it's a positive number. The absolute value of this is still this because they're all positive numbers. And the absolute value of this needs an absolute value sign because x could be a number that makes this negative. And this limit is n plus 1 times 1, because that's what this one is, times the absolute value of 2x minus 1. Oh, except here's the problem, right? The limit when n goes to infinity of something can't have an n left. So this is, the limit as n goes to infinity of n plus 1 times 1, which is what this limit is, times 2x minus 1, which is what this limit is. And this limit doesn't exist. It's infinity. Which means that there is only one value of x that will make this less than 1, because infinity is definitely more than 1, right? Greater than 1, right? Unless, it's equal to infinity, unless 2x minus 1 is 0. Because we technically multiplied by this before we did the limit. And so if we multiply that by 0, we'll get the limit of 0, in which case the limit as n goes to infinity of an plus 1 over an is 0, which is less than 1. So here we go. Ready? It never converges unless x is 1/2. Sorry. That's the problem with making things. Yep. So I put the absolute value in just here. And this didn't need one because it was a positive number. And this didn't need one because it was a positive number. But this number is allowed to be negative. So I have to put the absolute values there.
Limit as n goes to infinity of n plus 1. What's stopping us from dividing through by n?
Because it doesn't have a bottom.
Right.
So before, when I did this, I didn't actually divide by n. I divided the top of the fraction by n and divided the bottom of the fraction by n, which is the same as dividing by 1. But this isn't a fraction. If I wanted it to be a fraction, I could put a 1 there, and then I would get 1 plus 1 over n over 1 over n, which would be 1 divided by 0, which also doesn't exist. So yeah, that is an important question. So, right. So what this one means is that if this isn't 0, it doesn't converge, because the answer is infinity, which is more than 1. So in this one, I was very bad. The interval of convergence of this thing, what was it? Where's my original thing? N factorial over n squared plus 3, 2x minus 1 to the n is simply the number 1/2. Curly brackets because there's only one number there. That's the only number where it converges. Damn it, sorry people. Can we try a new one? I'm going to change this question just a little. And switch this fraction up the other way. Yep. So you've asked, go back to the alternating series and show the interval of convergence there. Yes, but only if I put an x to the power of n here. So if there's no x's, it can't have an interval of convergence because it's not a power series. But I can show that to you still. Actually, I'm only going to talk through this one. I'm not going to actually do it. This thing would be exactly the same as the other one, but the two fractions would be up the other way. So because this is upside down, this bit will be upside down, and this bit will be upside down. It'll be a 1/n plus 1. So when I do this working, the limit as n goes to infinity of an plus 1/an is going to come out to 1/n plus 1 damn it, there's still a limit, isn't there? Everything will be upside down. And this one, that limit's 1, that limit's 0, and that will be equal to 0, which is always less than 1 no matter what x is. Oh, crap. So converges for all x, which means the interval of convergence is the entire of the real numbers. Maybe this is not the best example to pick. I'm very, very sorry. I wanted to put a factorial in it, but it threw me off. Factorials tend to cause this thing to happen, and I really should have known that in advance. A factorial on the top, but not on the bottom, will tend to make the interval of convergence just one number. And a factorial on the bottom, but not the top, will tend to make the interval convergence everything. So sorry about that. Yep. Oh, I did have a... Which alternating series one was this? This one? So again, this doesn't have any x's. But we could make it a power series. Let's do that. So what if we had that? So what I've done is thinking this one here. What happens if that -1 came about because I put x equals 0 into my formula? That's what I can do. But this one I can't make an interval of convergence because it's not a power series. It doesn't have an x. So we definitely know it does converge when x is 0. So because of our previous work. Okay. Let's do this one here. So an plus 1/an. Sweet. Okay. Oh, yeah, I like this one. This one's good. Okay, I'm just going to leave this one as it is. So the limit as n goes to infinity of the absolute value of an plus 1 over an is going to be 1 times the absolute value of x minus 1. But just to be absolutely sure, I need the absolute value of this. The absolute value of that is the same as it was before. The absolute value of this is the same as what before because it's positive. And the absolute value of this is that. And that'll be 1 times. And this one doesn't change because it doesn't have an n in it. So the limit is whatever it is. So here we have an answer, finally, that isn't 0 and it isn't infinity. So the ratio test says, and I really should have said ratio test at the top. The ratio test says that if this answer comes out to be less than 1, then it converges. If this answer comes out to be more than 1, then it diverges. If this answer comes out to be exactly equal to 1, we don't know. So it will definitely converge when this answer is less than 1. The center is 1. So we're saying the distance between the center of 1 and x is less than 1. So here's the center 1. Here's a distance of 1 on either side. That gets me from 0 to 2. And so that's my interval of convergence from 0 to 2. But most people find it easier to talk about it like this. The absolute value of x minus 1 is less than 1. And that means that this number, whatever it is, has to be between minus 1 and plus 1. And if I add 1 to all 3 parts, I'll get 0, x, 2. So it definitely converges when x is between 0 and 2. The center of that interval is 1. That's good. That's what it should be. And the radius of that interval is also 1, which is a coincidence. Okay. So just to the picture of it here, here's 0, here's 1, here's 0, here's 1, here's 2. This is the interval we're thinking of. What we don't know at the moment is whether we have to fill in the 2 ends, because if x is exactly equal to 0, then this answer is exactly equal to 1. And the ratio test comes out to 1, which doesn't tell us anything. And if this is exactly equal to 2, then this answer comes out to 1. And so the ratio test again tells us nothing. And that's why you have to separately check the endpoints, because they're guaranteed to produce exactly 1 when you do the ratio test. Any number outside of this is guaranteed to produce more than 1 when you do the ratio test. And any number inside is guaranteed to produce less than 1. And so when we look at our diagram of convergence and divergence, it looks currently like this. We are absolutely certain that it definitely converges at all these places, diverges at all these places, and definitely converges at all these places. But what we don't know is what happens here. So we're going to have to check the endpoints. Check x equals 0. So when x equals 0, x minus 1 is minus 1, and the series is n equals 1 to infinity n minus 1 to the n over n 2n squared plus 1. And that converges because of the alternating series test. Which we did earlier. Which has its own working that you're supposed to do. Okay, so it definitely converges there when x is 0, and so we can color that one in, because it converges at that end. And now we check the other end when x is equal to 2. And then x minus 1 is equal to 1. And so the series becomes n equals 1 to infinity n 1 to the n over 2n squared plus 1. And you don't have the tools to tell whether that converges or not. But approximately, it's 1 over 2n, which is half of 1 over n, which is the harmonic series. Like n over 2n squared plus 1 is approximately equal to 1 over 2n plus, well, it's actually definitely equal to this, right? Divide everything by n, which is approximately a half times 1 over n when n is large. And the 1 over n is the harmonic series, which diverges. They will not give you one of these in Maths 1B exam. Yep. I couldn't hear that, sorry. So you're just saying when n is infinity, 1 over n becomes 0, yes? I said, yep. Because the terms going to 0 is not enough to make it converge. It has to go to 0 faster than that. The harmonic series is the classic example of it. If you add like a half plus a third plus a quarter plus a fifth, ignore the half and the third. No, I'll ignore the half. A third is more than a quarter. And so a half plus a third plus a quarter, I'll just do the running total, all right? So we have a half. I'm just going to do some parts of the running total. This is more than a quarter. And so far, this bit is more than half, and so this is more than 1, the running total. Let's do the next running total. This isn't the next running total, it's a little further down the line. But this bit, we already know is more than a half. And this bit, all of these are more than an eighth. 1/5 is more than an eighth, and 1/6 is more than an eighth, and 1/7 is more than an eighth. So this is more than a half as well. And so this is more than 1 1/2. And if I go to the next, go a few more running totals down the line, this bit's more than a half, this bit's more than a half, this bit is also more than a half. And so I get it being greater than 2. So no matter which number I think of, I can always make the running total long enough to get past that number. And so the harmonic series definitely diverges because the running total can be made as big as I want. And it's really hard to tell which series are going to do that. And my experience tells me that because the top is degree n and the bottom is degree n squared, and they're exactly 1 apart, this one will diverge. But they'll probably give you something else in, yeah. So I definitely know that it diverges at this spot. And so the interval of convergence is now, so this was just a sideline. So let me just say, since this is approximately like 1 on n plus a little tiny bit on the denominator, that little tiny bit on the denominator is not going to make much difference to this argument. So that's why. So therefore, the interval of convergence is from 0, including 0, because it converged at that end, and up to 2, but not including 2, because it diverged at that end. What's that? Well, the center is 1. The radius is the distance from the center to the edge. Well, it goes from 0 to 2. The center is 1. The distance from 1 to 2 is 1. Also, if you get it to this stage where it's the absolute value of x minus something less than whatever, that's the radius there as well. So if I had gotten this, then the radius would have been 7. Because this is saying the distance from the center 3 to the number x is less than 7. So right at the edge, the distance will be exactly equal to 7. Okay, so I've got a question in the chat. And the question in the chat said, what would happen if we wind up with infinity over infinity as n goes to infinity for a ratio test? And would that, can that even happen? It does happen. It happens all the time. If you see infinity over infinity, you have to rewrite it so that it's not infinity over infinity anymore. We did that here. That's infinity and that's infinity. We rewrote it so that it wasn't infinity over infinity anymore, but was in fact 1 over 1. Yes. So that's an important thing. In fact, that is the major and only tool we have, which is if you see infinity over infinity, you must do something else. You can use L'Hopital's rule. You can divide the top and bottom by something until it's not infinity anymore on both parts, but you have to change it into something that isn't infinity over infinity anymore, either by fraction manipulation or by L'Hopital's rule. You are allowed to use L'Hopital's rule here. Technically doesn't make sense because n is only allowed to be whole numbers, but you know, we just assume that the whole numbers are just one of some of the options for what n could have been. Yeah. Okay, that's intervals of convergence. So, what are people feeling about this at the moment and thinking about it? The important thing at this stage is feeling like you could attack this in an exam. You know, the important thing for me is that you feel like you understand it, but for the purposes of a major event happening within the next week, we need to know what to do with the exam. How are you feeling about that? I'm going to answer Bradley's question here. That's an important question. This limit at the moment looks like infinity divided by infinity. As n goes to infinity, that goes to infinity. As n goes to infinity, that goes to infinity. Now it sounds, if I can't know what to do with this until I make it not infinity over infinity anymore. So I'm going to divide the top and bottom by n. And now as n goes to infinity, this is 12. And as n goes to infinity, this is 3. And 12 divided by 3 is 4. So the limit of, if you have an infinity over infinity, it could be 4. And if this number was a different number, it could have been something else. So infinity over infinity could be any number at all. It could also be 0. It could also be infinity. But you can't know until you do this. Does that answer your question, Bradley? it is indeed very cool. Almost all of the coolest things in maths are about infinity. The other ones are about really small things that are just surprising that they're more complicated than you thought. So things like the angles of a triangle adding up to 180 degrees is just mind-bogglingly cool. Okay. Right. Give me a second. I have one more example to attempt to create. Okay. Bear with me. All right. Well, it's a bad example probably, but I'm going to give it a go. So I have the sum from when n equals 0 to infinity of an times x minus 2 to the power of n, where a0 is 1 and an plus 1 is 3an plus 1 over n. This is a recurrence relation sort of way of doing something. So we have not been told at all what an is as a formula. We're just told how each an is calculated from the one before it. The really cool thing about radiuses of convergence stuff is that I don't actually need to know what an is. I only need to know what an plus 1 divided by an is. So I'm going to do the ratio test. The limit as n goes to infinity of the absolute value of an plus 1 over an is the limit as n goes to, oh no, I'm just going to, wait. An plus 1 over an. Well, an plus 1 is 3 lots of an plus 1 over n. And now, if I divide everything by an, I'll get 3 plus 1 over n times an. So as long as an is increasing, this limit will be 0. So the limit as n goes to infinity of the absolute value of an plus 1 over an is the limit as n goes to infinity of 3 plus 1 over n times an, which is 3 plus 0, which is 3. Oh, except for the x's. Crap ass. Sorry. Oh, I shall call this B. I knew I'd confuse myself at some point. Right. So I called it Bn because I like an to be all of this. If your lecturer calls it an at that spot, it's all right to just put inverted commas here. So I'm just calling it an plus 1 over an. It's just not what you call an plus 1 over an. That would have been okay as well. Okay. And so we get this times x minus 2 times the absolute value of x minus 2 So I get this. And neatly, the recurrence relation just went away because I divided one term by the one before it. And so now, definitely converge when this answer that we just got is less than 1. And so the absolute value of x minus 2 is less than a third. So the radius is a third, and the center is 2. Damn it. Well, 2 minus a third. What's 2 in thirds? 6 thirds. So that's 5 thirds to 7 thirds, which works because it's it's 2 thirds wide, because the radius was a third, so the diameter is 2 thirds. And the picture here is that here is the center, which is 2, and we go up a third and down a third, and the answers are 5 thirds and 7 thirds. So it definitely converges everywhere in there. What we don't know about is what happens in the middle. Oh, sorry, not in the middle, at the edges. So when x is equal to the 5 thirds, that means that the x minus 2 is equal to minus a third. That'll always happen. It'll always be minus the radius at that end. And so the series is, no, we have no idea. We're not going to be able to tell. Sorry, because we don't know what the actual series Bn is. I'm not going to be able to. Can't do any of my other series tests, like the alternating series test and stuff, because I don't know. What was that? Thank you. Or maybe we do. That's just. It is an alternating series. Yeah? So to do the alternating series test, the terms individually would have to approach 0. Bn just gets bigger and bigger, doesn't it? Okay, just wait. So Bn plus 1 is 3Bn plus 1 over n, which is greater than 3Bn, which is greater than Bn. Because when you times a positive number by 3, it gets bigger. So it's bigger than 3Bn because the one on n is adding a little bit. And it's bigger than, yep, okay, so the terms are actually increasing. It can't converge. Oh no, crap, they're, because we're actually dividing by 3 though, aren't we? Like, because of the third there, it's not just the Bn, it's the, don't like it, Sam, I am. Because then the actual terms of these things, when I'm doing the alternating series test, it's everything except the minus 1 to the n. So I don't know. My instinct is it doesn't converge. Because if Bn is approximately 3, Bn plus 1 is approximately 3 times Bn. And so when you multiply, when you do several of the ones, you're going to get a 3 to the power n in there because you're going to keep multiplying by 3. There'll be some other crap over here, but oh, but this bit's like a harmonic series. I don't know. So I'm just going to stop there. If I was in an exam, I would say, if I was in an exam at this point, I would say, I need to check the endpoints to see if they converge. And so the options for the interval of convergence are either, there's 4 options. It either doesn't converge at both ends, or converges at that end, or it converges at that end, or it converges at both ends. This is what I would do in an exam if I didn't know what, if I didn't have time or I didn't know how to check the endpoints. I would just say, I need to check the endpoints to see if they converge. But whatever I do, there are 4 options for what the interval of convergence could be, and I'll just leave it at that. And that should be most of the marks. Yeah, I worry about things that are limits at infinity, and so I don't like it. So if all that does is confirm to you that the things with recurrence relations are hard, then yay, but you can at least do part of it now. Yeah. Yeah, probably. One of the tests from real analysis too. So yeah, you could compare it to some other thing. Because there's one with roots as well, you can compare it to. So yeah. Ratio test is a bust though, because we've already found the 2 ends where it is equal to 1, so we would have to do something else. That's enough of that, I think. I will happily keep talking for longer than I said I would, if you are happy for me to do so. But I will give myself a small breather where I will try and find my original list of what things we were supposed to be talking about today. Here it is. Might just do some random stuff, and some various things. So a few people mentioned directional derivatives. What is it about that is bothering anyone? Yep. Okay, so let me see if I can articulate that, both for me and for the people who couldn't hear that on the Zoom. There's all these different steps that need to be taken to do the calculations that are involved when there's partial derivatives and directional derivatives around. Yep, okay. All right. If I do one and then we look at what the steps were and try and pull them apart so we can tell the difference between them, that might be a helpful thing. Okay. So before I do that, I'm just going to talk for like 5 minutes. Am I right that in this course, they defined partial derivatives and talk about that before directional derivatives? Okay. So the problem is that directional derivatives are in fact the thing that we want when we're thinking about functions of multiple variables producing a number answer. So we have a function that takes R, whatever it is, but let's just pretend it's R3 today, Rn, and you produce a number as the answer. This is the kinds of functions that we're talking about. And I'm going to do R3, or R2 will do just as well. It doesn't really matter. What we want, let me just think a bit. So there's multiple problems. We have to know what original derivatives are, like of ordinary functions from numbers to numbers. So an ordinary function for numbers to numbers takes every number on a number line and attaches the output to that number. And so you'll have 0 and you'll figure out whatever number f of 0 is, and then there's a number attached there, and there's a number here which is f of 1, and there's a number here which is f of 2, and there's a number like, you know, everywhere. Like here there's f of 0.5, and every number has every number on the number line has an output attached to it. And normally we interpret those as heights and depths, and we draw a graph, right? And so you go, oh, f of 0 is like 4, and so you go 4 high, and f of 1 is 2, and f of 2 is -7, and then you sort of connect all those dots together and you get this lovely graph. Right. And in many situations, and that function normally represents, you know, often this x is actually time, and that function represents some number that is changing as time changes. But sometimes that x represents, in economics, it often represents the number of things that you produce in your factory, for example, or the number of things that you sell. Or the x could be the number of customers that you have. In economics, the x is often not time, but number of objects. Or it could be x is the price that you choose to sell something for, and the f is how many you sell. So if you make something more expensive, people will in general buy less of them. But it also depends on how expensive everybody else is selling it for, and blah, blah, blah. And if it's profit, you know, sometimes making more things uses up more resources, and there's this break-even point, and there's all this stuff that you can worry about. But you can ask yourself at a specific spot, here I am, if I change my x to be a little bit more, what does f do? Does it get bigger or smaller? So here's my value of f. If I go this way, will that make f go up or down? If I made x a little bit less, would that make f go up or down? And we don't normally ask this question, but it is a reasonable question to ask, especially in an economics point of view. You say, oh, maybe I'm making too many of these things and I should make less of them and I'll get a better profit. So there are lots of times in real life where you would like to know, if I change the x in one way or the other, what will the function value do? Will it go up or down? And how quickly will it go up or down? And that's what a derivative is trying to do. Okay. How are you feeling about general derivatives and the point of them? Sweet. Okay. What if there was more than one thing that you could change in your situation to change the profit? More than one thing you could change in your situation to change whatever the outcome is. In that case, perhaps here we are in R2, which is just being drawn as a plane because I can stand on it. Okay. And here's my x and here's my y. And here I am, and every one of these has a number attached to it. So maybe the x is how many the classic thing from Maths 1A with the optimization. You know, how many of Nutty Crunch do I make, and how many of plain do I make? You know, those sorts of things. And I'm asking myself, well, this is how many I've made of each. If I made a little bit more of one, a little bit less of the other, then that would be imagining moving in various directions here. And I'd like to know, what does the function value do when I move in those different directions? The directional derivative is the easiest way to think about what derivatives are doing. I'm just going to do this for a second. So imagine, here we are on, this is the space, and I have a little fly here buzzing around. And it's trying to find fresh meat to lay its eggs on. Right? well, fresh sweat to drink, right? And it can smell that, right? And the strength of that smell is a number that exists at every point in this room. Here it is here, and say, oh, it's not very strong here. Here it is here, it's much stronger. Here it is here, it's much stronger. And here it is here, it's much stronger. And the closer it is to any of you, the stronger the smell is. And so that strength of that smell is a number that is attached to every point in this room. And if your fly is here, it would like to know which direction should it go to make the strength of that smell strongest. Go that way, or that way, or that way, or that way, and that's what it will do. Mosquitoes work that way, but they're generally looking for concentration of carbon dioxide, because breathing animals make carbon dioxide, so I tend to follow that. So your function could be just a number attached to every point, rather than thinking of it as a graph. And then you can say, when I move in a particular direction, will that number be going up or down, and how quickly? That's what directional derivatives are about. How do people feel about that metaphor? Right. So that's all well and good, but what the hell, how do you figure that out? So what we assume is that if you only move a teeny tiny bit, all functions behave like matrices do, like constant multiples of things. So I'm just going to do it in 2D. So if we're here, what we're going to assume is that if we go a little bit in this direction, then what will happen is that the amount that the function value changes will be a multiple of this amount that we move. So if we move, maybe it'll be 3 times as fast as the speed at which I'm moving, that it will go up, or it'll go up, or it'll go down twice as fast, or it'll go up half as quickly. There'll be some number that I can multiply how far I go. It'll tell you how much the function value will change. And that will be true in every direction. And so what we're going to do is we're going to say, if we move a little bit this way, if we move this way, that's the same as moving a little bit this way and a little bit this way. And moving a little bit this way will make the function value go up or down a bit. And moving a bit this way will make the function value go up or down a bit. And that's what multivariable derivatives are about. So we're going to say, we're going to move along this in a constant fashion. And that I'm going to have a variable t to show how far across I'm going. And then I'm going to differentiate my big function in terms of t. That's what's going on. But ultimately, if I could draw a big graph of what this is, I'm trying to figure out how quickly it's moving. So that was bad, that bit, but I like the fly. I'll have to come back to that. So that's the goal. And I'm just going to talk about how to actually do it now. I'm going to hold that picture in my head. We're going to figure out how quick, the concept we're doing is that if you go in any direction, then you can figure out how fast the function changes by just using a few other directions. And it's very linear algebra. If you've got a basis, you can figure out everything else from the basis. So if I've got a function that sends, I'm going to do it in R3 to R, then what that means is it takes X, Y, Z, and it produces a number, single number as the answer. And so you'll have a formula involving X's and Y's and Z's. Tradition for mathematicians to put a bar on it when it's a single object going to a single object, whereas the arrow without a bar on the front is like the whole of R3 going somewhere. So in case you've ever seen the two notations, that's the rules. So what I'm going to do is I'm going to figure out how quickly it changes if I move in the X direction, how quickly it changes if I move in the Y direction, how quickly it changes if I move in the Z direction. And then I'm going to combine those three directions into a new vector, which is the direction I'm going to be actually moving. And so what's going to happen is I'm going to need, so if I want the directional derivative, I need more space. Of the function f in the direction of u at the point x naught, y naught, z naught. The notation for that is the directional derivative of the function f in the direction of u at the point x naught, y naught, z naught. So that's the directional derivative of f in the direction of u at the point there. So you see it, this is the noun, and these are all these prepositional phrases that modify the noun, if I want to go all grammar on us. And maths objects are constructed that way. I've done x naught, y naught, z naught because it's usually a specific point that you sub in. But if it was just x, y, z, it would be at a generic point and you'd have a formula of some sort. And what this is, this result is a number. And what this number tells you is how quickly f changes when you move in the direction of u 1 unit per second, basically. It's how quickly f changes relative to the speed that you're moving. All right. So here we go. Here's how to do it. The process to find it. The directional derivative of u, in the direction of u, of f at x, y, z is the gradient of f at the point x, y, z, which is a vector, dot with a unit vector in the direction of u. And when you do that dot product, it will produce a number, and that number is the directional derivative. Sweet. And to calculate this, I need to figure out the three partial derivatives of f with respect to the three variables. If it's only got two variables, I'll only do two of them. So let me do one. I just had to say this to myself so I had a clear idea of what's going on. Now we know how to pronounce this. This is the gradient vector of f at the point x, y, z, by the way, which is a vector. And it is a handy place to hold the three partial derivatives. So here we go. in the direction of, I don't know, 1, 4. At the point 2, 0. So just to make sure we know what's going on here we are at the point 2, 0. And the direction we're going is the same direction as 1, 4. So that's 1 across and 4 up, that direction. So if we start here and move past this point in that direction, then how quickly is this function value changing? That's what we're asking ourselves. So you could conceivably have a good estimate of what that would be. Just want to show you something actually. This is not something to do, but just to check your answer if it's working out correctly. So I know that f of 2, 0 is 0 times 2 squared minus e to the 0, which is -1. And if I go a teensy tiny bit in this direction, and I go 2.01, 0.04, like 0.01 times this and add that on, my calculator says that 0.04 times 2.01 squared minus e to the power of 0.04, and my calculator says that is this. Oh, it's very bright. Yay, okay. You can't see that, so I'm just going to, you're going to have to believe me that I did it right. Where's my E? So I know if I go in that direction, it's gone up a little. It was -1 and now it's -0.8. It's a little bit higher. So I'm expecting my directional derivative to be positive because when I go in that direction, it increases. And the directional derivative will be the amount that f changes by divided by the distance that I moved. That's what it's going to be. So the distance that I moved is, oh crap, Pythagoras' theorem, I'd have to do that. That's sad. So I'd have to do, all right, distance moved is the square root of 0.01 squared plus 0.04 squared, which is horrible. And the amount that f changes (0.120708), and so the change in f divided by the distance moved whoa, no, what am I doing? About 2.9. So I reckon that the directional derivative is going to be about 3. The amount that f changed by is about 3 times, is about 3 times the distance that I moved. But you would have to have, but we're doing this derivative-wise, it has to be a really small distance. But I just wanted to point out to you that this is what's going on. The tricky bit is this bit. I mean, it's all tricky, but the really tricky bit that makes it complicated is the fact that you have to divide by the actual distance you moved. I'm not dividing by the 0.01 or by the 0.04. I have to divide by the literal distance along this line that I went. And that's the problem. And that is why I need a unit vector. To make that unit vector, I have to divide by lengths of how long this vector is. Yeah. So that's just what's in my head of the literal calculations of what's in my head. If I go this far, how much does it change and how big is that relative to how far I moved? Okay. So let's actually do the calculation. To do the calculation, I need to find the gradient first. And to find the gradient, I need the derivatives. And so I need to do df on dx, which is, now let's see, the y is a constant that's multiplied on, because it counts as a constant for df on dx. Y is a constant multiplied on, so it will still be there, and then that'll multiply by that. This doesn't involve any x's, so it'll disappear entirely, because it counts as a constant. And df on dy, now the x squared is a constant multiplied on, so it's constant times y. The derivative of that is just the constant. And the derivative of e to the y is e to the y. So they're my two partial derivatives. So at the point 2, 0, we get that df on dx is 2 times 0 times 2, which is 0. And df on dy is 2 squared minus e to the 0, which is 4 minus 1, which is 3. Ah, look, we're doing well. Okay. Okay. So therefore, the gradient of f at the point 2, 0 is 0, 3. Are you okay with that calculation? How are we feeling? So the first part of the process is to figure out the gradient at the point you're interested in. And the first part of that step was figuring out the two derivatives and then calculating them at the point you're interested in, and then you've got a vector. Sorry? Yes, the gradient is a vector. Okay. So this vector is a handy place to hold the speed at which the function value would change if I moved in the x direction and if I moved in the y direction. Okay, so the next thing I need to do is find a unit vector. So this first step is finding the gradient. And now I want the unit vector. So first I'll just check if it is already a unit vector, and the answer is no, that is much longer than 1. Okay. But if it was already a unit vector, that'd be great. And if it's not a unit vector, I need to create a unit vector. So first I'll find the length of the vector 1, 4. Sure, and why shouldn't it be? And then I'll find the unit vector that I want is the vector that I had divided by that length. All right, so now I have a gradient, I have a unit vector, so now the directional derivative in the direction of 1, 4 of the function f at the point 2, 0 is the gradient, which was 0, 3, dot with the unit vector. So so I'll have 1 on root 17 times 0 times 1 plus 3 times 4 is 12, which is 12 on root 17, which is approximately 2.91. Look at that. Did you see? Did you see? Look at that. Look. 2.92. Oh, it's not far. Yes, the world makes sense. How are you feeling? So it can really help when you've got processes to give titles to the different sections. It helps me anyway, and it certainly helps the person reading your exam. So, and a happy marker is a generous marker. Right. So I will say that I have something else to ask you. What do you think the answer to this question would be? In this exact context, the same problem. What's the if the directional derivative in the direction of 1, 4 of f at 2, 0 is 2.91, what's the directional derivative in the direction of -1, -4 of f at 2, 0? Do you think? Sorry? Same? The reason it's minus, think of our fly. If the speed at which the smell is getting stronger when I go this way is 3, it should be getting weaker going the other way. And even with ordinary functions, if I've got a function with a slope of 3, if I go forwards, it will be going up 3 times as fast. If I go backwards, it'll be going down 3 times as fast. So if you go in the exact opposite direction, then the slope will be the exact opposite. The gradient will be the same at this spot, but the vector will be in the opposite direction. And so the dot product will be negative what it was before. That's just a useful thing to think about. I have another question. What direction should I go for my value of f to increase the quickest? That's an important question to ask. So here I am in this function here. I'm sure I drew a picture of this, just a second. If I'm at this point and I go in that direction, the directional derivative is 2.9. And if I went in go in this direction, it's minus 2.9. Oh, no, I have a separate question first. Okay. I know if I go this way, the directional derivative is 2.9, and this way it's minus 2.9. Which direction do you think I should go for the directional derivative to be 0? Perpendicular to this. Because if going from here to here goes between plus 2.9 and minus 2.9, it must be 0 somewhere in between. And the way that derivatives work is it's exactly halfway in between. Yeah. That's probably not true. Nope, ignore that. Not exactly halfway. It will be somewhere in between, but we don't know where. Not exactly halfway. Sorry, ignore that. It will be somewhere in between that it is 0, but we don't know which half it's in, except for one particular direction we know. But definitely somewhere in between it will be 0. So there will be a direction that the fly can go where the smell won't change. Okay. The other question is, well, if it's all different numbers here, it's between plus 2.9 and minus 2.9, it might actually go up a bit before it goes down. If I think about going in all different directions, it might go up to like 4 point something and then start coming down again, which is why we don't know where the middle is. So it might get faster in different directions. It might get slower. How are we going to tell which direction it goes the fastest? All right. Well, I can actually. What's that? Oh, anti-clockwise. Oh, well, not that. That's not what I mean. Not what direction should I move the arrow, but which arrow should I pick for the speed to change the fastest? I can do the speed changing 0. It's always going to be, the gradient at this spot is always 0.3, no matter which direction I face. If I want this answer to come out to 0, I need this vector to dot with that one to be 0. And if two vectors dot together to be 0, that means they're perpendicular. So to get the directional derivative to be 0, I need this vector to be perpendicular to that gradient vector, pretending it's a direction. And that's telling me that I really should actually start thinking about that gradient vector, not just as a place to hold derivatives, but also as a direction. So if I interpret the gradient vector 0, 3 as a direction, which is this direction, so I was at 0, 2, and I go that way, then that is the direction you should go to get the fastest derivative. Or greatest derivative, as fastest isn't. Oh, 0, 3 is that way. Oh, sorry. That's 2, 0. Thank you. I always get them the wrong way around. Well, almost always, but I can't tell which times it is. Okay. So let me just show you the directional derivative in the direction of 0, 3 of f at the point 2, 0 will be 0, 3 dot with a vector, a unit vector in the direction of 0, 3, which is 0, 1, which is 3. So unit vector in that direction. But you don't actually need to do this calculation. Not only is this vector the correct direction to go to get the fastest derivative, it's also the length of that vector is the fastest derivative. This is just one of the coolest magic tricks. So let me just do another one. Yeah, sure. I'm just making up stuff. This is a 3D function. It takes every point in 3D and produces a number. So at the point, say 1, 0, 5, what direction should you move to get the fastest increase for f? And that answer is the direction of the gradient vector. And what is the directional derivative in that direction? Okay, so if I'm going to calculate a directional derivative, no matter what, I need the gradient first. So df on dx is 2y. df on dy is 2x plus z cos y. df on dz, that doesn't have a z. That's the constant next to the z, which is sine y. And so at 105, df on dx is 2 times 0, which is 0. df on dy is 2 times 1 plus 5 times cos of 0, which is, now cos of 0 is 1, so that's 7. can I fit it? df on dz is sine of 0, which is also 0. Damn it, David. I didn't want them all to be 0. They're not all 0, but I didn't want 2 of them to be 0. That's okay. I'm just going to change my question. Sorry, I don't like my question at the moment. So I'm going to say plus x at the end, so that this becomes a plus 1 there. Okay, just wanted them to not all be 0. Wouldn't it be fun in your exam if you change the question? I don't like your question. I change it to this. My wife studied teaching, and one of her exams had one question, and it was, what did you learn this semester? Tough exam. Okay, and so the gradient of f at the point 105 is df on dx, which is 1, df on dy, which is 7, df on dz, which is 0. Okay. So normally, if you wanted to calculate a directional derivative, you would need to now find a unit vector in the direction you're going. But we don't currently know the direction we want to go yet. We need to find the correct direction that will give us the maximum directional derivative. And the correct direction is this direction. So the direction of maximum derivative is the direction of 170. That's the answer. I need to go in that direction, 1 in the x and 7 in the y and 0 in the z, and that will be the direction to go to make the value of f change the fastest. Yep. That was just for that specific example, the one that I did before, it was vertical. That was just because of that specific function happened to produce that answer. It is the maximum because, let me just think a bit here. The directional derivative in the direction of u of f at the point 105 will be 170, because that's the gradient, dot with a unit vector in the direction of u for this function. When you dot product two vectors, the answer gets bigger and smaller depending on what direction this vector faces. And if two vectors are pointing in the same direction, the dot product is the biggest it can be. And if they're at right angles, the dot product is 0. And if they're in opposite directions, the dot product is the most negative it can be. So if I want this answer to be the biggest answer it can possibly be, I need this vector to be in the same direction as this vector. That's why. And are you ready for the real magic trick? The real magic trick is the directional derivative in the direction of 170 of f at 105 should be 170 dot with a unit vector in the direction of 170. And the length of that vector will be the length of 170. So only in the situation when you happen to be moving in the same direction as the gradient, the directional derivative will be the length of the gradient. So this will be root 1 squared plus 7 squared plus 0 squared, which is root 50. Which if we really wanted, we could say that that was 5 root 2, but that's not really any better. You know, it's going to be like 7 point something. So you do not, in this one situation, is the only situation when you're finding a directional derivative that you don't have to find a unit vector first. Yeah. And if I went in the exact opposite direction at -1, 0, -5, then that would be the greatest negative derivative, like the negative derivative of greatest size. And so if this f represented the height of we're in 3D. Ignore all of that. Like if this represented gravitational potential, then you would go in the direction of the greatest negative thing because things move to lower potential energy. So in physics, that's what they use it for. Directional derivatives and gradients are used to tell which direction things are going to go. That's one of the things they use it for. I mean, physics, electromagnetism in particular, like vector calculus, which is what we're getting close to here, was invented precisely for the purpose of doing electromagnetism in physics. It was invented by physicists. But back in those days, there wasn't much of a difference between physicists and mathematicians. And not that there is these days either. It's very common for people to do a physics degree and then switch over and do their PhD in maths instead. So there you go. How are we feeling about those directional derivatives? Yeah. So they're very cool. And to me, they make more sense than the other derivatives. So this partial derivative is also a directional derivative technically. This one here, this here is saying that if I move in the direction of 1, 0, 0, which is where the x-axis direction, then that's the speed at which it's going, at which the function value is changing. Yeah. So if you do multivariable calculus 2 in the future, or vector calculus and electromagnetism, if you're in electrical and electronic engineering, some of these ideas will come back. So, you know, otherwise you'll just have to think about them in your own time and think that was a pleasant thing. Sweet. I like directional derivatives. Let me think about this. I'll do it in 2D instead of 3D if that's okay. So this is going to be the gradient at the particular point I'm thinking of. And I'm going to try all different vectors. So these are going to be my different u hats. So when I do the dot product of two vectors, the dot product of something with a unit vector is the length of the projection of your vector onto that unit vector. So that's a linear algebra thing. So if I do the gradient of f dotted with this vector, then that length there is gradient of f dot u hat. And if I did gradient of f dot with this vector, that length there would be gradient of f dot with u hat. So if they're at exactly right angles, the answer will be 0. But the closer this vector is to this vector, the longer this projection is going to be. And that's why. Because we're going to be, because no matter what u is, to find the gradient, to find the directional derivative, we're going to have to dot u with the gradient. And the closer the gradient, the u is to the gradient, the bigger that projection is going to be. Yeah. And the other maths reason is that it will be the length of the gradient of f times the length of u times cos of the angle between them. That's the formula for the length of the dot product. And cos theta is biggest when theta is 0. And when theta is 0, the two vectors are the same vector. Yeah. Yeah. So what we're keeping, yeah, we're keeping this vector fixed and changing the thing we're projecting it onto. And so if you want to choose the thing you project onto to make the projection the longest, then that you should pick the thing that you started with. Yeah. Yeah. So, so in 3D, there should actually be, in 3D, if this is the gradient in space going wherever it goes, there should actually be like a whole all these vectors perpendicular to all of them give you a directional derivative of 0 because they're all perpendicular to the gradient. And just a final thing, if the gradient is 0, 0, 0, then no matter what direction you go, the directional derivative will be 0. And so as you move past that point, the function value doesn't change. And we know what happens with ordinary functions. If you're at a point where they move past it, the function value change, that makes it a maximum or a minimum. And so you didn't get up to that in this course. It was the last week. But if the gradient is 0, then that means that the directional derivative is 0 in every direction. And you must be, if in 2D, at the top of a hill or the bottom of a valley. Well, possibly in very rare circumstances in the middle of a Pringle, where if you go one way, it's a minimum, and if you go the other way, it's a maximum. But we can get into that another day. But yeah, so basically in 1 dimensions, you need one derivative to be 0 to be at a maximum or minimum. In 3D, you need all 3 derivatives to be 0 simultaneously to get a maximum or a minimum. So yeah, just to add to that. Big fan of directional derivatives. Partly because it was a long, hard road winning, understanding what they were, because again, it was one of the things in first year that didn't make sense. So I tend to like the things the most that didn't make sense for a while, but I still figured them out anyway, and then they did. That's bizarre. It's not happening on my computer, so it's in this computer. He's just getting tired. Okay, I really am going to stop now. That's quite enough. I've had enough. I'll stop the recording.